Hello, I'm Max Mercer, and welcome to the lesson about matrix representations of linear transformations. Please recall an earlier example where we looked at the outcome of left multiplying by a matrix. What we saw was that the entire grid scaled proportionally. This is a critical property of linearity that makes it possible for us to have a matrix that represents any linear transformation in Euclidean space. So the special property is that we really only need to find out where the basis vectors land from the standard basis, and then we really understand the whole transformation if it's linear. So here's the theorem. Let L be a linear transformation from n dimensions to m dimensions. Then there is a specific matrix A that is m by n. Here the amount of columns is the dimension of the input space since we're left multiplying. And this matrix, the first column is going to be the output of the linear transformation applied to E1, which is 1, 0, 0, and so on. It's the first standard basis vector. The second column of the matrix A is going to be the output of the second standard basis vector, and so on up until the nth standard basis vector. Now let's prove that theorem. Any vector x can be broken down into how many first components it has times E1 plus how many second components it has times E2 plus so on, so on. Recall, we've already defined linearity in a specific way. Linearity means the image of a linear combination of vectors is the linear combination of those individual vectors' images. We use that right here for our proof. By linearity, we can pull the transformation L inside the sum, just like our definition, and then where the columns are the mappings of the standard basis vectors, we have exactly the matrix vector product we wanted all along, AX. Now let's see an example of finding a matrix representation for a linear transformation. We're given a function L that takes a vector from 3D space, because see we have 3 coordinates in the input vector, and maps it to 2D space because we only have x1 and x2, no x3 coordinate anymore. Alright, so the rule here is that the top entry becomes the sum of the first 2 components, x1 and x2, while the bottom entry is fixed at 0. So since we're mapping from 3 dimensions to 2 dimensions, our matrix A must be size 2 by 3. To find the specific entries of the matrix, we apply the transformation to the standard basis vectors. For the first column, we input the vector 1, 0, 0. According to our rule, 1 plus 0 is 1, so the output is the vector 1, 0. For the second column, what do we get when we input the vector 0, 1, 0? Well, 0 plus 1 is 1, so we get the vector 1, 0 again. For the third column, we input 0, 0, 1. The sum is 0, so the output is the 0 vector. Now, right away, we can assemble these 3 resulting vectors into the columns of matrix A. As you can see by the color coding, the first column is 1, 0, and the second column is also 1, 0, and the third column is 0, 0. This matrix A now defines the transformation for any vector x in R3. Here's our example 2. We have a slightly more complex rule this time, but you're going to be great at it. Our function L takes a vector with components x1, x2, and x3 as input. It outputs a 2D vector where the top entry is the difference x2 minus x1, and the bottom entry is x3 minus x2. Just like before, mapping 3D inputs to 2D outputs means we're looking for a 2 by 3 matrix. So we find the columns by plugging in the standard basis vectors. For the first column of the matrix, we see what we get when we input 1, 0, 0. The top entry becomes 0 minus 1, which is negative 1. The bottom is 0. For the second column, we input 0, 1, 0. The top is 1 minus 0, giving us 1. The bottom is 0 minus 1, giving us negative 1. Finally, for the third column, we input 0, 0, 1. The top is 0, and bottom 1 minus 0 is 1. So we take these 3 result vectors and arrange them side by side to form matrix A, as we take them as columns. You can see the columns are negative 1, 0, 1, negative 1, and 0, 1, exactly as we had above. This matrix now represents that difference rule for any input vector in 3D space. Let's work together on the next example. Here we define a transformation L from R2 to R2 that is supposed to reflect vectors across the horizontal axis, or the x1 axis. Since we're starting in 2D and ending in 2D, we know our transformation matrix A must be a 2 by 2 grid. Okay, so as always, the secret to finding the matrix is to see where the basis vectors go. First, look at E1, the vector 1, 0. Since it lies exactly on the reflection axis, it doesn't move at all. It maps itself to itself, 1, 0. This becomes the first column of our matrix. Now look at E2, the vector 0, 1, pointing straight up. When reflected across the horizontal axis, it now points straight down. It maps to 0 in x and then -1 in y. All right, this becomes our second column, 0, -1. So we take those two result vectors and place them side by side to build our matrix A. It has the top row of 1, 0 and bottom row of 0, -1. When we apply this matrix to a general vector x with components x1 and x2, the matrix multiplication leaves x1 alone, but flips the sign of x2, which is exactly the reflection formula we wanted. Finally, let's find out, is this matrix invertible? Mathematically, the determinant is -1. Since that is not 0, the answer must be yes. But think about it geometrically. If you reflect a vector over a line, can you go back? Yes, you reflect it over the same line again, because doing the same action twice brings you back to the start, the identity matrix. The inverse of the matrix is actually the matrix itself for this specific reflection matrix style. Now for example 4, we define a transformation L that reflects vectors across the diagonal line x2 equals x1, or as we'd normally say y equals x. Since we're mapping 2D to 2D, our matrix will again be 2 by 2. Okay, so we'll track the basis vectors and see where they end up to find our columns of the matrix. So E1, 1, 0, if we're going to reflect across the line y equals x, we end up at 0, 1. Then E2, 0, 1, if we reflect it, we end up back at 1, 0. And so we assemble matrix A using these results as columns. The first column is 0, 1, and the second one is 1, 0. This creates a matrix that functions as a coordinate swapper. When applied to a general vector x1, x2, the output is x2, x1. So geometrically, it's the same thing as flipping coordinates across the diagonal. And this is also an invertible transformation, and therefore an invertible matrix. The determinant is -1. Again, that's non-zero, so we know right away our matrix is invertible. Geometrically, this is intuitive. If you swap your x and y coordinates and then swap back, you get back to the original vector. Therefore, the transformation is actually, again, its own inverse. Now for example 5, we have something different. Instead of reflecting, we're doing an orthogonal projection onto that same diagonal line, x2 equals x1. Imagine shining a light perpendicular to the line and seeing where the shadows of our vectors fall. First, look at E1, the vector 1, 0. Its shadow hits the line exactly halfway between the axes, and it maps to the point 0.5, 0.5. Now do the same looking at where 0, 1 maps to. Also, if we're mapping it onto the line y equals x orthogonally, it's going to end up at 0.5, 0.5. And so we build the matrix A. It will have actually the first and second columns identical to each other because both standard basis vectors 1, 0 and 0, 1 map to the same output point, 0.5, 0.5. And so when we apply this to a general vector x, we get a formula that simply averages the inputs, and that's the output in both x and y. All right, so is this invertible? Not in this case. And we could see that because the matrix's determinant is 0. And so geometrically, we have squished a two-dimensional plane onto a one-dimensional line. We have destroyed information, so we cannot reverse the process. For example, if we say, okay, our output is 0.5, 0.5, what was the input? Well, we can't know if our input was 1, 0 or 0, 1 or even -1, 2 or any other point that would project onto this output point. So we can't go back. We destroyed that information. There's no inverse for this transformation. And so another fun thing is that if you project a vector that's already on the line, it stays there, right? So this means applying the matrix twice is the same as applying it once. So a squared equals a, and you could check that. If you do a times a, you get itself. For the next example, we have a transformation that now rotates vectors in the plane by 90 degrees, or pi over 2 radians, in a clockwise way. All right, so that's going to go clockwise. I have a little diagram here to show clockwise and counterclockwise. It follows the hands of a clock if it's clockwise. All right, this maps two-dimensional space to two-dimensional space. So the matrix A will be 2 by 2. All right, so the first column of A is where the first basis vector is mapped to. If we were to rotate the first basis vector 1, 0 by 90 degrees, we would end up directly down at 0, negative 1. And then the second column of our matrix A is going to be where our second standard basis vector 0, 1 maps to. Doing that rotation, we should end up at 1, 0. And so we can build the matrix exactly like this, stacking columns side by side. Okay, and then if we apply this to a general input vector x1, x2, our output vector is going to be x2 and negative x1. So you could see immediately, okay, that's how the coordinates are going to change. We're going to put x2 up top and then x1 on the bottom and make it negative. That's exactly what it means to do a 90-degree rotation clockwise in two-dimensional space. Okay, and so finally, a fun question, is this matrix invertible? Yes, it is. The determinant of A is 1. That's non-zero, so the matrix is invertible. And so geometrically, what can we do to invert this transformation of rotating 90 degrees clockwise? Well, we rotate 90 degrees counterclockwise. We go right back to the start. All right, so since we can return to the start, we don't lose information in the process. This transformation is invertible. Now, let's see how we can build a rotation matrix for any angle theta. Let's do counterclockwise this time because the picture is quite nice, but we'll generalize it to clockwise as well. So all we need to do for these matrices to get them is to track what happens to our standard basis vectors. Okay, in our input space, we start with a purple vector pointing at 1, 0 and a blue vector pointing at 0, 1. Okay, so when we rotate the entire plane counterclockwise by theta radians, let's see how that results in the output space. Here we have, for example, angle theta, both here and here. We've rotated the purple vector to now land here and the blue vector to now land here. All right, we rotate about the origin. Okay, and so because the columns of the matrix tell us exactly where the basis vectors land, we can define our rotation matrix A by finding the coordinate points for these new vectors, this new purple and new blue. All right, so let's zoom in on the geometry to find those coordinates. If we look at the rotated purple vector, which was originally our x-axis, it forms a right triangle that becomes clear if we draw dots. Okay, so using trigonometry, the horizontal side is the cosine of theta, and the vertical side is the sine of theta. This gives us our first column of the matrix. Let me show you exactly how that goes. We find A11 because cosine is supposed to be adjacent over hypotenuse, right? That's adjacent over hypotenuse. We're using standard basis vectors. This is just like vectors on the unit circle. So the hypotenuse is 1. A number divided by 1 is itself. Okay, so cosine of theta is A11 and sine of theta is A21. And now we can also find, for this rotated blue vector, it's also a right triangle, but the lengths have some good relationships with each other that we can find our answers using. So A12 is the same length as A21, but negative, right? Because it's on the negative side of the x-axis. So it's going to be negative A21, which is negative sine of theta. All right, and then A22 to find where 0, 1 ends up the y-coordinate of that vector. That's going to be the same length as A11, both positive this time, though, because y is positive going up, right? So A22 is A11, which is also cosine of theta. Therefore, we can build our matrix now because we know the first column of the matrix is where 1, 0 is mapped to after applying this rotation by theta radians counterclockwise, right? That's going to be cosine theta, sine of theta, that's this point right here. And then here, the second column is where 0, 1 maps to after rotation by theta radians as well, counterclockwise. That's going to be negative sine of theta, cosine theta, that's this point right here. And so we got our general counterclockwise rotation matrix, which works for any angle theta. By convention, we'll just say a theta is strictly larger than 0. Now that we have a formula for counterclockwise rotation, what happens if we'd like to go the other way? Let's figure it out and build our matrix for clockwise rotation. Imagine we want to rotate clockwise by an angle phi. Alright, geometrically rotating clockwise by phi lands us in the exact same spot as rotating counterclockwise by angle 2 pi minus phi. Alright, so if we have 2 pi minus theta, that's going to be the same as rotation in the other direction by phi. Alright, and so because we already have a general rotation formula, we can just plug phi into our existing matrix. By substituting 2 pi minus theta for phi everywhere in all 4 spots, we get a new matrix expressed in terms of theta. To simplify this, we need to remember a couple of properties of sine and cosine. Let's look first at the graph of cosine, okay? That's this graph here in blue. Now, if you compare the value at any point x to the value at 2 pi minus x, you see they have the exact same height on the graph, okay? And so this means the cosine of 2 pi minus theta is exactly the same as cosine of theta itself. Now you could do the same thing for the graph of sine. Here the values are actually mirror images. Okay, so I have in blue the graph of sine of x, and then we have sine of 2 pi minus x in red. Notice that for every input x in 0 to 2 pi, sine of x has the flipped sine y output of sine of 2 pi minus x. So if we want sine of 2 pi minus theta, like we do here and here, we just need to do negative sine of theta. When we plug these identities back into our matrix, the signs shift. The top right becomes positive sine, and the bottom left becomes negative sine. Interestingly, this results in the transpose of our original counterclockwise matrix. It's also the inverse of matrix A, which should make sense because it's just rotating space with the opposite angle. We'll talk more about orthogonal matrices where the inverse equals the transpose later on. What we want today is this final formula for a clockwise rotation. Here are 3 practice examples to get comfortable building rotation matrices. At the top, we have our 2 standard templates, matrix A for counterclockwise rotation and matrix B for clockwise rotation. Example 1 asks us to rotate any vector by 45 degrees in the counterclockwise direction. 45 degrees is equivalent to pi over 4 radians. Since we're moving counterclockwise, we plug this angle into the matrix A template, and the cosine and sine of pi over 4 are both root 2 over 2. And so we fill those values in, keeping the negative sign in the top right corner as required by the formula. Okay, now let's pause and analyze what this matrix actually does. If you left multiply this matrix to any vector, for example 1, 0, you're going to rotate that vector by 45 degrees counterclockwise, right? So 1, 0 is here. If we rotate it 45 degrees about the origin, counterclockwise, we end up at pi over 4 radians. So the output of that standard basis vector 1, 0 is root 2 over 2, root 2 over 2. That's exactly the first column of the matrix. Same thing here. You could do the same thing with 0, 1. If you rotate that 45 degrees counterclockwise, you do end up exactly where you're expecting at the point, negative root 2 over 2, and then positive root 2 over 2. Okay? For example 2, we're rotating clockwise now by pi over 6 radians. Because the direction is clockwise, we use matrix B this time. Okay, so the cosine of pi over 6 is going to be root 3 over 2, and the sine is 1/2. We plug those right into the template, and then, how lovely, we notice that for our clockwise rotations, the negative sign shifts to the bottom left position, all right? And so remember, this matrix B is A transpose. Okay, if you're using the same angle theta. All right, so here let's see why that makes sense. If we're rotating pi over 6 radians clockwise, that's going to be 30-degree angle, right? And we're going clockwise. So we're going to go down from the point 1, 0, down to root 3 over 2, negative 1/2. That's our first column, isn't it? And then same thing here. If we start with the second standard basis vector, 0, 1, we're going to rotate clockwise and end up at 1/2 root 3 over 2. That's our second column. How beautiful. All right, so example 3 combines actually 2 steps. It is a clockwise rotation by pi over 6 radians, again, same as before, and then also a reflection over the x1 axis. Okay, so now instead of multiplying matrices, we can just track where the basis vectors land. That's how these matrices operate with this column view of matrix vector multiplication. Okay, so first, please look at the vector 1, 0. If we're going to rotate it first, remember that ends up at root 3 over 2, negative 1/2. All right, and then if we're reflecting this over the x1 axis, the horizontal axis, we end up at root 3 over 2, 1/2. All right, that's exactly going to be the first column of our matrix C. Now the second point, 0, 1, if we were to rotate this by pi over 6 radians clockwise, we end up here at 1/2 root 3 over 2, right? And then we reflect it over the x-axis and we end up at 1/2 negative root 3 over 2, right? And that's our second column of the matrix. This gives us our final matrix C. All right, so we just solved example 3 by visually tracking the basis vectors, and that's great for intuition. What we did is we saw where the basis vectors ended up and made those the columns of our final matrix, okay? But we could also use this composition shortcut I talked about once before, but I talked about it a little informally. So let's say we have two linear transformations, S and T. S from vector space U to vector space V is represented by a matrix B, let's say, and T is represented by a matrix A. That's from V. Notice the input space of T is the output space of S. They have to be the same space for this to really make sense. And so here we're still outputting to W. If we apply T to the output of S, we get the composition T of S. All right, this is just like functional composition. Maybe you've seen f of g for functions. This is for transformations. Linear transformations, specifically T of S here. Now, the matrix of the composition T of S is the product of the representation matrices A, B. All right, so here's what's going on. Because we apply the rotation first, for example, let's talk about our example. That is going to be closest to the input vector x. All right, so if B happens first, then that has to be rightmost in this expression. And then A will be to the left of Bx because we apply A second after that. Okay, so here, let's pull up those matrices from our prior work. We have matrix B, our clockwise rotation matrix. How lovely. This is actually from example 2, right? And also a previous example where we got the matrix for reflection over the horizontal axis. Okay, if we multiply A times B, doing the row by column operations, we output a single matrix. And if you compare this result to what we got at the top, notice they're exactly the same. Okay, so this confirms that matrix multiplication, this specific matrix multiplication, is the correct way to chain these steps together. All right, and so to check quickly, the matrix A being diagonal, how beautiful, tells us to take one row of B, and that's our new first row, and then negative second row of B, that's our new second row. How cool is that? We got exactly the same result by two intuitive ways. We could either do a composition of transformations, because we've already seen both of these, or we could follow the basis vectors, and then their columns are where those basis vectors end up. Here's a neat composition example I'd love to share with you. We start with our standard rotation matrix A. Now, what if we wanted to rotate by twice as much of an angle, by double the angle, or 2 theta? Well, we simply substitute 2 theta into our template, and this gives us matrix B on the right. Okay, but there's a second way to think about this. Rotating by 2 theta is physically the same as rotating by theta and then rotating by theta again immediately after. This is a composition of A with itself. So we get the result on this line here. Okay, if we multiply A by A, we get A squared. That should be equal to B because they're the same physical transformation. So the matrices representing them must be equal. The matrix for 2 theta is equal to the matrix for A squared. Okay? Now, we can just equate the corresponding entries. If we look at the bottom left terms, we find out sine of 2 theta must equal 2 sine cosine. That's exactly one of our special identities, right? If we look at the cosine terms in the top left, we get cosine of 2 theta equals cosine squared minus sine squared. Guess who? Exactly what we talked about before. This is a wonderful realization. All right, so here's kind of the heart of this point. Trigonometry is not just a list of random rules to memorize. These identities come directly from the beautiful properties of linear algebra. All right, so now I have a new example for you, a challenge example about linear transformations on other vector spaces. This might look a little intimidating because it involves calculus, but the process is identical to our geometric examples. We just need to track where do our basis vectors land. So let's say we're talking about P2, where I'll define the set of polynomials up to and including degree 2. Okay, so this will be any linear combination of 1, t, and t squared, where t is the variable. All right, so here we feed the number 1, our first basis vector, into our function here, our linear transformation. So we're mapping a function to 2 times the function's derivative plus 3 times the function. The derivative of 1 is 0, so the output is going to be 2 times 0 plus 3 times the original function 1. That's 3, which if we wanted to write in this a new basis, 1t and t squared is going to be 3, 0, 0. That's 3 1's plus 0 t's plus 0 t squareds. 3, 0, 0, the coordinates of this. All right, now let's feed in t. The derivative of t is 1. All right, so we plug that into the formula to get 2 plus 3t, right? And so, writing that as a vector, we get 2, 3, 0, and that's our going to be our second column right there, 2, 3, 0. Now we want to see where does our third basis vector end up applying this transformation. Well, the derivative of t squared is 2t, so the output becomes 2 times the derivative 2t plus 3 times the original function t squared, so that's 4t plus 3t squared. Writing this in this new basis notation is going to be 0 1's plus 4t's plus 3t squared, so our third column is going to be 0, 4, 3. Now all we have to do is put these columns together side by side and we get our matrix A. We have now successfully converted a derivative function into a matrix, all right? So why do we want to do this? Why is this so special? Because now we can solve calculus problems using only multiplication. Okay, so if we want to transform, for example, this complex polynomial, we just turn its coefficients into a vector and multiply. Okay, so if we wanted, for example, what's going to be this function 5t squared minus 3t plus 4, if we wanted to get 2 times its derivative plus 3 times the original function, all you have to do is do a matrix multiplication. This one's quite nice. For example, 3 times 4 plus 2 times negative 3 plus 0 times 5, going to give us 12 minus 6, which is 6, right? Same thing for all the other ones. You do get 15t squared plus 11t plus 6. How cool is that? And because I love to show you, I love to give you the evidence. I give the calculus result perfectly. The derivative of this function, what is it? Going to be 10t minus 3, right? 2 times that derivative plus 3 times the original function. If you want to work it out, you get how many t squareds? 15 of them. How many t's? 2 times 10, so 20 minus 9 t's, right? 11 total t's. And then negative 6 plus 12. That's going to be 6. That's exactly the similar operation we had here, right? 12 minus 6. It was in the different order, but remember, when we have addition, it's scalars, right? So it's going to be commutative, no problem. Now let's take these joys and move them into 3 dimensions, all right? So we're looking at a projection transformation. This time it flattens all of 3D space onto just the XZ plane. So here I have X, Y, and Z. Notice any Y is going to be squished onto 0, right? So visually, think of this like stepping on a soda can or just shining a light to cast a shadow. All right, to build the matrix, what do? We track our 3 basis vectors, just like before, and we see where do they end up in the output. All right, so the red vector, this on the x-axis is going to be 1, 0, 0. That's perfectly fine. That's on the xz plane already, so if we're going to project it onto that, it's onto itself. So that's the first column as well. The output is going to be same, 1, 0, 0. Now this green vector, 0, 0, 1, that points along the y-axis. It gets squished completely to 0. So here we'll have this situation where the second column is going to be just zeros. The third column is the z-axis. That's perfectly fine. That's projected onto itself, so it's still going to be 0, 0, 1. Okay, so here's our matrix A. Putting those outcomes as columns side by side gives us this matrix. And so this is a great example to visualize the kernel in the image of the transformation. The kernel is everything that got destroyed by the transformation and now maps to 0. Okay, since the y-axis, anything on the y-axis, anything in the span of 0, 1, 0, any multiple of this second basis vector, that is going to map to 0, right? Because we're squishing the entire y dimension. And so that is going to be the null space of the matrix A, right? This is going to be the y-axis is the null space. And so the kernel of L is the null space of A. Remember, L is the linear transformation represented by left multiplying by matrix A. And so that's going to be just the vector 0, 1, 0. Okay, so if you want the basis for these, all you have to do is get rid of the span and just take any vector inside of this. So here, 0, 1, 0. Now, same thing here. To find the image, possible outputs of the linear transformation, that's the column space of A, all right? So any linear combination of columns of A, that's going to be span of anything, any amount in the x direction plus any amount in the z direction. So if you wanted a basis for the column space, you just get rid of the span. This is now the basis, 1, 0, 0, and 0, 0, 1. But to get the entire column space of A, the matrix, or the image of L, the transformation, same thing. It's going to be this whole plane that's the span of those 2 directions. All right, so that's going to be all amounts of x and z and 0, y. Okay, great job. Now let's look at an example of reflection. Specifically, we're reflecting all of 3D space over the YZ plane, okay? So you think of a wall formed by the green and blue axis as a mirror, okay? So when we look at our 3 standard basis vectors, the green y vector and the blue z vector don't move, all right? They're exactly where they're going to be reflected to already, so they stay exactly the same. However, the red vector x points straight into the mirror, so it's going to turn into the negative direction. We're going to have -1 in the first column of matrix A, -1, 0, 0. And so here's our matrix A. Just like always, we put the columns as the outputs of the standard basis vectors under the linear transformation in that exact order. Okay, so now let's compare this to that projection we just did. In the last example, we flattened the cube. And so here the cube is still a cube, all right? It's just a little backwards over this mirror, right? So we haven't lost any dimensions or squashed anything to 0 besides 0, which has to be squashed to 0 under linear transformation, right? So because of that, the only thing in the kernel is 0, 0, 0, all right? And the image is the entire 3D space. Excellent job. I hope you have a wonderful day.